Hi everyone, welcome back to Ethics, Analytics, and the Duty of Care. I'm Stephen Downs. We're in Module 7, the decisions we make, focused on AI workflows and the decisions made as we apply AI and analytics to education and development. Today's video is entitled Tools and Algorithms, and we're going to be looking at some of the mechanisms that are used by AI and analytics developers in order to create the kinds of tools that we're using in learning analytics. This is a big subject, and I'm going to try to do it in less than an hour. Hopefully less than, well, maybe not less than half an hour. And obviously I'm going to be gliding over the details. I'm not going to get into the many algorithms that have been developed over the years. The tools and algorithms I will talk about are ones that have been developed a while ago and are now regarded as classics in the field. And the intent here isn't to teach you artificial intelligence. That's not going to happen. But it is to give you a sense of the range of decisions that gets made on a day-to-day basis while these tools are being developed and applied in real-world situations. And that's why I begin with this particular quote from Zimmermann et al. In 2020. Developers cannot just ask, what do I need to do to fix my algorithm? They must rather ask, how does my algorithm interact with society at large, and as it currently is, including its structural inequalities? We're not designing AI algorithms and learning technology for some abstract future where everything is hunky-dory. We live in an existing, flawed human world, and the tools we use will reflect that, and we have to ask, how do we make them better given that reality? Now, we're not going to answer that question either in this presentation, but we'll inch forward bit by bit and try to come up with an answer to this overall in the course. So I'm going to be using terms a bit loosely during this talk, and indeed I have throughout the course. Strictly speaking, there are different terms we could use for different things. Artificial intelligence is a very broad field, developed, well, after the Second World War. It developed almost with the beginning of computer technology. And basically, it's any technology designed to emulate human intelligence. That includes a lot of a lot of rule-based algorithms, expert systems, stuff like that mostly we're not talking about. Machine learning kind of began in the 1980s. It's a subset of artificial intelligence where instead of us telling machines what to do, we began to think about how machines could learn on their own. Now, sometimes this includes neural networks, sometimes it doesn't. It's all very fuzzy. It doesn't really matter, but we need to keep that in mind. Deep learning has been around, I think it got popular around 2010 or so. The concept has been around since the neural networks work that was done in the 1980s, but really it didn't take off until we got the processor power that would make it possible. Deep learning is, for the most part, neural network learning, and as I'll say later on in the presentation, the deep in deep learning comes from the idea that there are multiple layers of processing that takes place, the deep referring to the number of layers. So neural networks are mostly about deep learning, but they do kind of extend into machine learning as well outside, because you can have like one layer neural networks, as we've seen, perceptrons, right? Now, strictly speaking, perceptrons are a kind of machine learning. You see why the terminology is kind of messy. don't sweat the terminology, really. My perspective is each one of these tools, each one of these algorithms is a thing in itself. We can classify them and categorize them all we want, but really there's one thing, then there's another thing, then there's another thing, then there's another thing. And that's probably the best way to look at it. All right, so speaking of categorizing, machine learning is generally broken down into three major subcategories: supervised, unsupervised, and reinforcement. Supervised machine learning uses labeled data sets. So we have data, and each bit of data has a label. These labels are created by humans. So for example, it might be a string of numbers, and a human said that's temperature. Or it might be a string of values, and humans say that's house prices. You get the idea? So with supervised machine learning, we use the data with the labels, and that produces output, and then a human critic looks at the output and decides whether it's acceptable or not, and then feeds back any error into the system. We saw an example of that in the earlier presentation on backpropagation, and backpropagation is typically thought of as the paradigm instance of supervised learning, and it does go all the way back to the 1980s. Unsupervised learning is data without labels. Now, could have labels, but we don't care in this case. And what the machine is trying to do is discover hidden patterns in the data without human intervention. Now, there are different ways to do that. So really, the human intervention in this case is in the design of the network itself and the functions in the network and how the neurons interact with each other. But there's nobody looking at the output, if there is even indeed an output, and saying, yes, this is good, no, that is bad. That's why we call it unsupervised. Reinforcement is kind of like supervised, but we're not saying that an error has been necessarily found. What we're doing is we're applying machine learning within a context, like a game, say. And the state of affairs of the game is fed back in to the machine learning algorithm, and then it uses that in order to correct what it's doing. So those are the three major types. Really, it breaks down into two, right? One in which some kind of external experience corrects the machine, and the other in which the machine kind of learns on its own. All right. So machine learning, as I said, goes back a while. There's a couple of examples I want to talk about here. I won't linger on them, although I could, that are types of machine learning, but they're not neural networks. One of them is Kmeans. The idea of Kmeans is to take some data and organize it into clusters. So imagine you have a bunch of data points. It could be a time, temperature, or whatever, right? Represent that on a two-dimensional graph, much like the one we see pictured here. Now, what we want to do is draw circles around the clusters of the data. Maybe not circles necessarily, but we want to organize the data into clusters. How many clusters? K. So maybe 2, maybe 4, maybe as many clusters as there are individual data points. That would be like perfect clustering, but we never do that. So what we do is we present that data, we pick a couple of points called centroids, and then we cluster all of the data points around those centroids according to a couple of rules or principles. One is, which centroid is the most close to the data point itself. So that'll break it down into two groups. And then we try another centroid, another pair of centroids, and create clusters again. We keep trying it a bunch of times, and what we're going to try to do is pick the best clustering. Well, what counts as best? Well, perhaps one way of counting the best is the longest distance in our graph here between the two centroids. We can see on the diagram that we have here, they're pretty far apart. It would be pretty hard to imagine that they were further apart given these points. Another way of looking at it might be the tightness of the cluster, right? How close are the individual data points to the centroid? So these are decisions we make on picking the best way of clustering these individual data points. And here comes the train. Because I have no control over my environment. All right, here's another type of machine learning. Again, it's for clustering, but it's kind of like predicting clustering. So let's say we have a bunch of data points sitting on a graph, and they've already been identified as this type of thing or that type of thing. So we've produced some clusters. We can see the clusters there on the graph. And now we have a new data point, and we wonder, what kind of data point is this? Well, what we do is we look at the closest data point. So here on the right hand side, here's our new data point. The closest data point is a red triangle. So we could group it as red triangles. Well, we don't have to just pick the closest. We could pick the closest two data points. Still red triangle. Okay, well, what if we do the closest three data points? Well, two red triangles and one blue square. Okay, so we're still going to call it a red triangle. What if we took the closest five data points? Now we have three blue squares and two red triangles. So now we might want to call this a data point of the type blue square. So the size of the circle here, or in other words, the number of data points we will look at, k data points, really matters. So when we're using nearest neighbor, that's the sort of decision that we want to look at, right? How close or how broad should these circles be? What size of k, in other words, are we going to use? That'll produce different results for new data points. And, it really depends on how these things are organized. With both Kmeans and k-nearest neighbors, these data points are plotted on the graph according to their features. So we need to pick out what features are relevant to plot them on the graph. And in fact, we might even decide to use a bunch of different features and different graphs and then average them out or something like that. Or maybe have them compete against each other, whatever. There's different ways of looking at that. All of these are design decisions. It's almost like an art, right? Because you try these different design decisions and then see if the results are really what you think they ought to be. If this diagram here classified my green dot as a yellow circle, I'd really wonder about that. And I'd say, no, that's not really the result that I'm looking for. So in all of these cases, the machine learning or the neural network involved in the deep learning is going to have to do some learning. It's going to have to reorganize the relations between or the connections between the data points. And I'm using the term data points a little bit loosely here, but by a data point, what I mean basically is the value of, in this case, one neuron in the network. Or it might be one piece of input. It's a little bit loose here. But what we're doing here in these learning algorithms is basically reorganizing the weight of the connections, or perhaps the bias of the activation function, or maybe messing with the activation function itself, etc. They're all ways in which the machine learning algorithm or the neural network can reshape itself in response to feedback either internally or from the environment. So there's a bunch of different learning algorithms, and just as an aside, when people say, what is a learning theory, these are things that I think of as learning theories. Educators talk about learning theories a lot, and they'll talk about, social constructivism or something like that. But those aren't how things learn, whether machines or otherwise, right? Social constructivism isn't a description of how a person learns. It's a description of an entire educational and pedagogical approach that hopefully gets people to learn. But I think of a learning theorem, or as I've described here, a learning algorithm, as the story we have that explains exactly what's going on as the connections between individual neurons or the associations between different data points are shaped and reshaped by, whatever the learning theory says reshapes them. So let's look at a few of these. So this is the oldest and in many ways the best. It's called Hebbian learning. People have heard me talking about Hebbian learning for, decades. It's often summarized as cells that fire together, wire together. So suppose we have a neural network, here it is, and we present some phenomenon to the neural network that results in a certain number of cells firing. You might think of this as an input layer maybe, or maybe a hidden layer, whatever. Okay? So these neurons are all connected to each other, but what is the strength of these connections? Well, what we can say is, if two cells, I tried to click on it. If two cells fire together, then we create or strengthen the connection between them. If two cells fire together here, if two cells fire together here, you see we're going to draw lines, basically connecting the red dots and strengthening that. If a different set of neurons fire, then we'll draw the connections differently. And so here we'd be connecting the green dots. That's all it means. That's what it is, basically, right? So things that fire together, wire together. They become associated with each other. And that's pretty neat, because if you fire a whole, if you draw all these connections whenever these green dots fire, then suppose maybe 2/3 of them fire. Well, we're probably going to, because the connections are so strong, induce the firing of the remaining dots. So that's called a partial activation. And so we can create an experience as though it were the whole set of green dots by a partial activation of some of the green dots. Hebbian learning. That was anticipated as far back as David Hume. When things happen together, we tend to associate them together. That is, Hume said, how we develop concepts like cause and effect, or necessary connection, or personal identity. The second one we've talked about already in one of the previous presentations. It's called backpropagation. So in backpropagation, as we discussed before in quite a bit more detail than we will here, errors are measured by a human, presumably, typically, and then a correction is sent back through the network so that each layer assumes part of the responsibility for the error in the output. The mechanism by which that happens is called a descent function or something like that. And basically, we're just looking at the slope of the difference between the result that we wanted and the result that we got. That's all I'll say about that. I talked about that earlier. Group method of data handling isn't one thing, it's a bunch of things. So it's kind of hard to get your handle on it. But basically, what we're trying to do is lighten the load for neural network engines. There are all kinds of ways of doing that. I'm not going to get into the details of those because I'd spend the rest of the talk trying to get into the details of those. But here's an example of what GMDH might do for you. Here's the complete graph that we have at the start of GMDH processing. It looks at those connections that'll really actually be relevant to whatever it is that we're trying to produce. For example, we're really interested in this particular data point as an output. Forget the other stuff. So that means we're only going to be interested in the connections that lead to that data point, which really produces kind of a subset of the overall neural network for us. Why would we do that? Well, processing the optimum graph here, as it's called, is going to be a lot whole complete graph. As well, we might be able to emphasize some types of data in the optimum graph calculations on the whole complete graph. So there's a bunch of, like I said, there's a bunch of different methods. These algorithms bring in a whole set of factors that allow us to tweak how we look at the learning process in one of these networks. And so each one of those, and no time for a discussion of them, but each one of those may have ethical implications, or maybe not. Competitive learning is interesting. And what happens here, this is kind of, I mean, it's a type of unsupervised learning, although it can also be used in supervised learning. And basically, we have our nodes in layers, just like before, but in a given layer, the nodes are connected to each other. And the firing of one layer might prompt or inhibit the firing of another, the firing of one neuron, one unit in this layer might prompt or amplify or inhibit the firing of another one in the same layer. So in a sense, the individual units in a layer are competing with each other for the right to be basically the one neuron that eventually is the neuron that fires in that layer. And the usefulness of this is that over time, and possibly with training, these will tend to, each neuron will tend to focus on a characteristic set of input. So they'll be what we call feature detectors. So if X1 and X2 fire and Xn does not, that might prompt 1 to fire. And 2, meanwhile, might gain the upper hand if X2 and Xn fire and X1 does not. And similarly with M down here. So the competitive learning is a way the machine learns how to handle the input data on its own simply by feeding back information from the same layer that's doing the processing. Pretty neat idea. Neuro Evolution isn't technically a part of deep learning or neural networks, but basically the idea here is to use what are called evolutionary algorithms in order to generate neural networks, neural network parameters, topologies, and rules. So Basically the genetic algorithm will respond to perhaps environmental conditions or other variables out there in the world, for example, k-fold, cross-validation, etc. And what this will do is it will actually change the design, what we're calling here a meta model, of the neural network that we're going to use to apply to a particular problem. So it's kind of like, it's inspired by evolution, right? As the name suggests. And similarly, humans went through centuries, millennia of evolution, and over that time, human neural networks evolved, and not the individual neural networks, but the overall design of human neural networks. We've got the visual cortex in the back and the hippocampus and all of the different brain components and the way neurons in general link to each other, the two hemispheres of the brain connected by a corpus callosum, all of that was shaped by evolution. And so, similarly, perhaps the actual design, the topography of a neural network could also be shaped by evolutionary factors. So there's a variety of approaches and a lot of work done on evolutionary algorithms. I've listed a whole bunch of resources here. Now, the sorts of decisions that we'll be looking at here is, what counts as an evolutionary factor? How does an evolutionary factor interact with the design of a neural network? There's a validation and testing process that happens. What is a good test for a meta model? And what is an irrelevant test for a meta model? Questions like that come up, and the answers to those depend partially on what you're trying to do and partially by what you think evolution is. Is it really just a random process? Is it a directed process in some way toward a better, toward a goal like a better human, a smarter human? There are different approaches to evolution. Even things like the difference between Darwinian and Lamarckian in evolution, right? Are we evolving physical features only, or are there contents like, say, archetypes, ideas that also pass down from generation to generation? Really interesting questions here. The Boltzmann Machine is my personal favorite, just because I love the elegance of it. And the idea here is that you have a neural network, kind of an interesting way to design one here, but again, they could have different topographies. And what you're trying to do is, for a given set of activations, so for values of u here being 1 or 0, you want to set up your connection weights so that it achieves the lowest possible kinetic energy. So what will happen is that, and it's nicely described in a Jeffrey Hinton video, which I'll link to a little bit later, but you keep adjusting your connection weights and then shake it up a bit and then adjust it again and shake it up a bit and adjust it again until you've settled into the lowest possible state. I like to think of it by analogy as what happens, for example, when you throw a stone into a pond. And that messes up the water, but then the water will ripple for a while, but eventually it'll settle down into its stable state. Now, what's interesting about this, how that happens depends a lot on the nature of the stone and the nature of the water, and we could think of different ways of creating these so that you get different results. Throwing a stone into water in zero gravity probably wouldn't work at all. So the amount of gravity that we have also matters. But also too, we can come up with different definitions as to what we think is a stable state. I'll be talking about attractors later on, and you get a visual representation of that. So those are some of the learning theories. It's not all of the learning theories, but it's not even necessarily all of the most important learning theories. But the idea to get across here is that there are different kinds of learning theories. In my talks in the past, I've basically focused on Hebbian contiguity, which I didn't really mention here, but it's similar to competitive pools. Back propagation and Boltzmann mechanisms. And those have been the four that I've emphasized over the years as the way we learn, as humans, the kinds of mechanisms that we use to learn. It doesn't translate nicely and directly into learning or pedagogical practice, and nor either does it translate nicely and neatly into ethical and non-ethical behaviors. However, the sorts of decisions we make, given these different kinds of approaches to learning that we might invoke in this or that circumstance, may have pedagogical or ethical implications. Another set of decisions concerns the topology, or the organization of the network. And there's two major kinds of topologies. A physical topology, which is the actual physical organization of the network itself, and then a logical topology, which shows how data flows within a network. For our purposes, we can just think of them as one and the same, but obviously there might be logical topologies within larger physical topologies. There might be multiple logical topologies within a single physical topology. Think, for example, the way mail flows in through a company. The physical topology is all of the people connected to each other in the company. So it might look like this fully connected topology, or maybe a star topology or a tree topology if it's a hierarchy. But the information won't flow equally to everyone. An email that comes into the company might flow up and then stop. An email that comes into a company might flow to 3 or 4 people and then stop. So the logical topology can be different from the physical topology. Topologies matter a lot. The way you construct your network really influences how your network behaves. A fully connected network is going to behave very differently from a line. I'll give you a simple example. Suppose you have a virus and it has a 50% chance of being passed on from one person to the next. Well, if we have a line, this person has the virus, there's a 50% chance of it being passed on to the next person, which means only a 25% chance of being passed on to the next person, and so on. The probability gets lower and lower and lower, so it's almost impossible that the last person is going to catch the virus. Meanwhile, look at our fully connected network. If this person has a virus with a 50% chance of being passed along, well, there's 1, 2, 3, there's 5 individual connections. So that basically means that the odds of this being passed along are really good. I'm not going to do the calculation off the top of my head, but I think they're just virtually certain. 50%, 50%, 50%, 50%. I think you just add them. That would make it more than 1. That can't be it. I'm sure there's a calculation. I just don't know it off the top of my head. But anyhow, if you even pass it off to one person, right? Now this person and the original has the virus, and they also have a 50% chance of passing it along. So they probably, well, anyhow, everyone's going to get it, right? So that's really different. With the ring, well, the virus could go in one of two directions. With the mesh, it could go, in this case, depending on who gets it, right, in one of three. So, basically, the topology influences the propagation of a signal through the network. Makes it important. There's a lot of topologies. I'm going to look at a few that use some of these topologies. I'm not going to cover all of them because that would be crazy. But remember, here's the perceptron that we talked about way back at the beginning. Here's an ordinary feed-forward network with one layer. Here's a deep network with multiple layers. And there are other types. Here's a Boltzmann machine that I talked about, which is a fully connected network in this case, but which is using a specific algorithm to weigh the connections. So here's the feed-forward neural network. This will be the first of the topologies that I'm going to look at. I'll look at a few. And as we saw, it's a network where the data flows into the network and then out the other end. It's like, the perceptron or the multi-layer perceptron are examples of feed-forward neural networks. And this internal layer, there may be one, there may be more than one, will do the processing for us. Something called a radial basis network is organized differently by means of changing the activation function. You notice how this activation function doesn't look like the ones that we talked about in the previous presentation. Previously, it was either a square or single jump, or later on we talked about the sigmoid curve. This kind of activation function has a point at the middle and declines at each end. And what that means is that we're dividing the possible states of affair here not into two, but into three. Right? A 0 if it's too low, a 1 if it's in that middle value, and a 0 if it's too high. This allows us to do to organize data not just using a line or single line, whether it's straight or curved, but by using non-linear classifiers. For example, here we have a case where this x was too low, this x was too high, but these O's were perfect. Similarly, here's the center corresponding to the top of our activation function, and these are all the data points around it. So by changing the activation function, we can change how we do classification in our data. That's really important. Because if that's true, now let's think about that for a minute. There's an infinite number of ways we could define that activation function. Every one of those is going to treat the data differently. Now, there's no obvious ethical implications to treating the data one way as opposed to another way. Although, if you view the world as nothing but sigmoid functions, it's either this or that, then you can't do all of logic. So, and if you can't do all of logic, that seems to be a weakness, might be a problem with the system that you're using. So, and that's one of the things that led to the development of radial basis networks. If you want to do a logical operation like exclusive OR, for example, then you need this kind of network and not a simple perceptron. This is a convolutional neural network, and it's a fascinating thing. So Suppose we're processing an image that's represented by all the green squares here on the left-hand side. And what we want to do with this image is identify different features in the image. If you remember from the presentation we did near the beginning of this module, we were recognizing different numbers. Do you remember that? And we were recognizing numbers first by picking out the strokes or the circles, so detecting the features and then combining the features so that they were parts of numbers, and then identifying the number. Well, this is how you do that. So basically, you work your way through the input data with a subset, but looking at it subset by subset. Basically, what you're doing here is you're taking what we call a kernel filter and applying it over and over and over to different sections of the input data. So this filter is looking for an X. Can you see the X there in that diagram? Right. So what you do is you apply it to the top 3x3 part of this matrix, and then you multiply the filter by the values in the matrix. That gives you a result, in this case 4, and then you map out all of the results. And that way you're doing feature detecting for this particular filter on this particular data. Now you could apply this, use different filters. So take your image data, make a couple dozen copies of it, and then apply different filters to each one of those. Create one of these individual grids, and in fact, you probably want to pool this so it's just one single number, and then put that into a competitive neural network layer, and then feed that forward. You've got a really reliable feature detector, and that's what these things are used for. So at first glance, the definition of the kernel filter seems completely arbitrary, and it is, right? It's just ones and zeros here, right? 1, 0, 1, 0, 1, 0, 1, 0, 1. That's the feature that we're looking for. But the question is, what do these ones and zeros stand for? What are the ones and zeros in this input data? In a typical image, it might be the 3 primary colors, right? So we'd have three squares, each one representing one of the primary colors. So what are they? Red, cyan, and yellow, or something like that. I can never remember. Once they introduced cyan to it, I was lost. I'm old school, right? Red, yellow, and blue. Those were my primary colors. Anyhow, I also think there were only 6 colors in a rainbow. So there. That was one for Andrea, who believes that there are 7. Anyhow, what do those ones and zeros stand for? What are you detecting with those? Are you detecting simply dots in a sensory apparatus like a camera? What is your camera looking at? Where is it pointed? What is the focus? Is it large? Is it narrow? Is it a micro camera? Is it testing for infrared and ultraviolet as well? Maybe it's got a filter on the camera, so it's doing heat detection. Maybe, and this is an interesting application, what's feeding into this matrix here is data that you've already processed, for example, by looking for what's called gradient descent. So what you're doing there is you're looking for if you've got cases of a high value and a low value. So then you have a high gradient descent as compared to cases where the two values are close together. You have low gradient descent. That allows you to detect edges. So this might be a gradient descent matrix that now we're analyzing with this filter in order to find features. So that's an edge detection used to do feature recognition. That's very similar to how the human visual cortex actually works as well. where the edge detection plays a major role in how we recognize objects in the environment. So take this, combine it with a time sequence detector so that we can persist data over time, and now we're well on the way to picking out objects in the world, aren't we? So recurrent neural networks use the output from one neuron as the input for another. This is the basis for the competitive pool networks that I talked about earlier. This is the basis for Boltzmann machines as well, where neurons feed back into each other. So a fully recurrent neural network will connect all of the neurons to each other. But usually we have simple recurrent neural networks where we just take one layer of the neural network to feed it back into each other. This allows us to think about things like, well, long short-term memory. Let's see what the cognitive psychologists do with that, right? They love their short-term memory and cognitive load and all of that. So basically, this is the time sequence detection that I talked about just a few moments ago, where it can process data that comes in sequentially and keep its hidden state over time. So, see we have H coming in at time -1 and coming out of here as HT, and then that'll feed back into HT -1 for a new HT, etc. So, as you can see, the network's feeding back into itself here so that it can keep this hidden state through time. And so this is useful for things like detecting handwriting, detecting speech, finding anomalies, where the one thing depends on the next thing, depends on the next thing, depends on the next thing. And you wouldn't be able to detect those unless you had something like an LTSM in order to do that. So this tan-H and this, I'm not sure what that is. Is that, it's not a sigma, it's not an omega, it's something. It's, please don't say it's an omicron. These are activation functions again. So tan-H, so we had sigmoid, we had the bell curve kind of thing, and now this tan-H is another kind of activation function. Hop field networks, sometimes talked about under the heading of spin glass, have been around since forever, well, since 1982, and basically combines the idea of LTSM with, or LSTM with Boltzmann machines. This is the one that's described by Jeffrey Hinton in this really nice video. I do recommend that you watch it. And the idea here is that memories could be, he suggests, energy minima of a neural net. So what's happening here is that the hop field net is storing a pattern, and then it uses that pattern in order to recall the full patterns based on partial input, the way I talked about before. So what you're doing is you're trying to achieve a state of minimal energy. So what you're going to do is, here you have these different values, ones and zeros, but now what you do is you work through these one at a time. You just pick one at random and ask yourself, what would the value be given everything else? So here's a 1 here. Let's turn this into a question mark and ask, well, what would the value be? Well, it's, 1 times 3 plus 2 times 1 is 5. So 5 is above 0, so we'll give that a 1. Let's move over here to this 0. Let's make that a question mark. What would the value be? Well, 1 times -4 is -4, plus 1 times 3 is 3, so that's minus 1, plus 3 times 0 is 0. It's still minus 1, so that's below 0. We'll leave it as a 0, and so on. And basically the idea is that you get this stable state when you get this number, well, the way I've been doing it, as high as possible, because this number corresponds to the negative energy. So the higher this number is, the lower the energy state is in this neuron, or in this neural network. And so that's how it stores its memory. We have the weights of these connections, which are basically telling us what this memory should be. This memory is the lowest energy state. Now, I just drew a little parabola there, or an upside down parabola. And so the lowest energy state would be the minimum, right? Of course, that's in a nice simple world. In the real life, you might get ups and downs. You might even have a three-dimensional field which has different minimal points that define what your lowest energy state is. And it even depends on how you're defining energy, how you're setting these weights, how you're writing these activation functions. All of those impact how you think of your lowest energy state. Still, neat idea. Now, people don't really use these anymore, but the concept hasn't gone away. It does give us a step toward what might be called an attractor network. Remember, I talked about different ways of finding these lowest energy states. Well, let's define those as attractors. And so, just brief aside, all of chaos theory. Throw that into the mix. So now these are my attractors instead of, just a single lowest point defining my most stable state. Here I'm defining lowest points on this grid, or this two-dimensional, three-dimensional matrix. So there are different minima that I could be working toward. Here's a couple, here's one, or on this one, here's one, here's one. So as I calculate the different values for these neurons, I'm looking for the values that will lead us to this lowest possible state. So I'm going to do some random calculations, work out what all the values are plotted on this graph. Do some random calculations, work out where all the values are plotted on this graph. And what I'm going to do is actually trace a path through the graph, as I move toward that lowest energy value. And so that's how my attractor network works, and that's also how the process of this attractor network reaching that lowest possible can be described. And you have these paths that actually look like the attractors that you see in chaos theory, because they won't go they don't go straight to the lowest point. They'll usually sort of circle it and then zero in on it. So there are different ways of defining these. These may represent real world conditions. They may represent changing environments over time. There's any number of things that these could represent. In this particular example here, we're looking at cell sequencing, cell proliferation, cell death. I know nothing about cell sequencing and proliferation and death, frankly, but that's the sort of thing. This is the P53 regulatory network. So we're using these networks to determine whether there's going to be DNA damage, reparable DNA damage, or irreparable DNA damage to this particular regulatory network. Fascinating stuff, but you can see how the real world application of this feeds directly back into how we're how we're designing these internal properties of these networks, these incredibly complex internal properties of these networks. So this actually may represent an actual set of physical connections between, say, cells or DNA strands or whatever in a human body, and now we're predicting as a result of some external influence or just the state that they find themselves in. So as I mentioned before, deep learning is taking all of these things and actually running it through multiple layers. So we talked about edge detection and feature detection a little bit earlier. That's how this process works, right? So we have perhaps in our input layer a bunch of light and dark pixels. Now our next layer might identify the edges. So, we're doing gradient descent or something like that. Then in the middle, we're going to find combinations of edges, which tells us where we found an eye or a nose, or I don't know what that is. And that lets us build up bigger features like the full nose, left and right eye. Still don't know what those are. What could those be? I have no idea. And then that eventually allows us to recognize, oh, it's the top of the head and it's the chin. Okay. And then combining those allows us to pick from a set of possible outcomes what we think this input is. And in this case, the input is George Washington. The output here is George. This is really important because in certain very significant respects, you can't recognize George unless you already have some idea of what George looks like. So, recognition isn't something that just happens automatically. It isn't inherent in this data. This data all by itself isn't going to tell you that it's George. You need to recognize it as George in some way. We can say that this input corresponds to this output, and that's all just ones and zeros, right? This set of ones and zeros corresponds to this set of ones and zeros. But from our perspective, we need to be able to say this set of ones and zeros actually is George. So that's an important limitation on how we can interpret the reasoning that's conducted by artificial intelligence and neural networks. All right, one more thing and we're done. Frameworks. Now, part of the reason I was slow with this particular presentation is I thought I should look at the current state of some of these frameworks. Well, there's no such thing as just looking at the current state of some of these frameworks. First of all, look at them all. We have Google Machine Learning Kit, Open Neural Networks, Auto Machine Learning, etc. I messed around with TensorFlow the other day, and I also messed around some with Scikit. Most of these are written in Python. Some of them are written in C. None of them are written in languages that I'm happy and comfortable with, which is a real problem for me, and is a real problem for people in the world at large, right? If you're doing machine learning, really you need to be comfortable with Python. Really comfortable with Python. And this is a language, similarly with some other languages, where it really matters a lot which version you're using. For example, I installed the most recent distribution of Python on my computer in order to work with TensorFlow, not realizing that, TensorFlow, I installed 3.10, the latest version. TensorFlow works between, I forget what it was exactly, but something like 3.5 and 3.7. So I couldn't run TensorFlow on my version of Python. Also, a lot of these machine learning and neural network applications will load whole libraries. For example, matplotlib, which is a library that actually creates those graphs for you. Or there's I forget what it's called. It's basically it's numbers for Python. It's not scikit, but anyhow, whatever it is, there's a specific whole framework for machine learning calculations in Python. It's SciPy or something like that. I'd have to look it up. So this all goes to say that developing and using these machine language or machine learning and neural network or deep learning applications, the learning theories, the patterns, the design, the activation functions, the topographies. This isn't something that you and I and pretty much everyone watching this video are doing. It's a very specialized discipline. And that inherently carries with it risks. Any discipline that's really specialized will carry with it inherent risks. The club of people who are expert in nuclear systems is very small and might be not looking at the long-term effects or even outside their own discipline. It takes a lifetime to master all of this. You don't have time to study all of the history of philosophy or pedagogical implications and theories from the 1950s on. It's just not going to be part of your education. And so consequently, this is why we say things like we need diverse teams working on these applications, because it takes so much to learn these things. You've seen some of the detail, right? That the people who learn how to make these AI engines run aren't going to be the people who have a deep and informed understanding of, say, the ethics of care or contract theory, or pedagogy, social constructivism, connectivism, the rest. There's going to be different groups of people with different bodies of knowledge. That's the nature of knowledge. I mean, the connectivist system is like that too. Any neural network is like that, where each neuron in the network has its own thing that it's doing, and only the network as a whole does things like recognizes George Washington. There's no individual neuron that's the George Washington recognizer. Just like there's no piece in my head that is the knowledge that is Paris is the capital of France. It's all distributed in the connections in my head. So that's one thing. The other thing is that this discipline is still incredibly in flux. You don't necessarily get that sense reading it in the newspapers, reading about it in the newspapers, but you really do get that sense actually trying to work with some of these tools. A lot of the time, they just simply don't work, right? Now, of course, they all do work, but you can't just install them on your computer like Microsoft Word and it takes off. Generally, and as a solid piece of advice here, I would say use something like a cloud container, like a Docker container, where it's all pre-installed and ready to run. Now, there's a gazillion decisions have already been made in designing that particular container with that particular framework to run those particular algorithms. All that work's been done. And so, in a sense, if you use one of these containers, you're viewing the world from the same perspective as the designer of those containers. Nonetheless, it's going to take you years to learn how to design that perspective for yourself. So this is a case where, when people talk about having a theoretical lens to look at the world where that actually makes sense. But it's not theory in the sense of constructivism or whatever, right? It's theory in the sense of here is a neural network tool or framework contained in a container that I will use to run this data through. So you could either install it as a Docker container, or what's also becoming popular is that these are just made available as services by large companies. For example, I demonstrated at a talk I did a while ago. I fed one of these AI recognizers by Microsoft. I fed it in an image and it sent me back a caption, right? So I just had a little bit of JavaScript on my side, and it had this great big AI with high processing power on its side. So there's a cost to that, obviously. Although in this case it was a demo, so I was able to do it for free. But if I tried to do that in production, now I'm going to get a cost. But if I run it on my own machine, well, there's still going to be a cost, but then it's a trade-off, right? And now I'm doing economic trade-offs and not just processing or algorithm decision-making trade-offs. You look at any of these, and you will immediately see what I mean. You will see that this is really hard to do, almost impossible for an individual person to do from scratch, although you might be able to support that as an organizational capacity in a larger organization, and is going to impose a way of looking at the world, but not a simple kind of lens like critical race theory or something like that. There's no such thing as a Docker container containing machine learning algorithms that is critical race theory informed. I mean, it's really is comparing letters to oranges. They're just completely different kinds of things. But there is a theoretical perspective. Look at this image here, right? There's a theoretical perspective here. Look what's important. The big orange thing, the little red things, and these tall green things, right? And then this purple thing. So we know that the objective here is to keep the blue thing on the purple thing and to avoid the orange, red, and green things. But that's not all that there is to driving, right? And there's whole swaths of the world not covered by orange, red, and green things. And that's the kind of perspective that's brought to bear here. That's the, I don't want to say bias, because bias is the wrong word. It doesn't even make sense to say bias anymore in this sort of context. So that's the tools and algorithms presentation. Took me a bit to get this one out, but I'm glad I did. And I want to stop for a year and go back and keep doing this presentation until I'm happy with it. But I can't. I got to move on. We've got to move on. The world's not going to wait for us. So I'm going to move on. Next presentation, we need to talk about models and interpretations. And I'm going to throw a whole bunch of other stuff into the mix. The mix is, just like I said during the summary for this module, we're not taking into account 5, 10, 20 factors when we're making an ethical decision using artificial intelligence or as an intelligence ourselves. We're taking into account thousands, tens of thousands, 60,000 features. You look at this and you can see how that could be the case. And that's what I'm trying to show in this presentation. So that's it. I'm Stephen Downs. Talk to you next time.